The class just started. I don't want to sit in there. I was going to go sit in the room so I don't have to listen to dogs barking, everybody playing. Is it on?
Mm-hmm. Yeah, but it didn't start very well, so I thought you might want to sit in there anyway before you close the door.
Which one are you trying to start?
The one in the office.
I don't want to sit in the office.
Okay, well, will you please start it for me because I'm asking you to. Yes, honey. Daddy has a call for.
Is that one? Oh, that's that one. Okay. What am I doing here? Should I get this tripod out of the way? Yeah, it's all right. We can leave it here. It's all right. Hey, George. Hello, everybody.
How we doing?
Fine, man. Fine.
All right.
Wait a minute. I want to give you ultimate power here. Hang on a second. Make host. Yes, you are the host. Host with the most. Thank you very much.
I'm the host.
You are the host. So when I need help with an illustration or something, you're the man.
How does that work?
Oh, you haven't done it before. That's right.
No.
John usually does it. That's right. Why, Chris Lawrence? Why are you doing a screen capture? Don't do that.
You know, I'm not. There's no wipe on that switch either. It's
one thing you could do is rotate that tall post until it's pushed. Go a little bit further and stop. So that you pushed that top switch, that E switch. Go a little bit further, a little bit more, all the way to the peak of that formed blade. Okay, stop there. Now bend the short blade of that top switch so that it's about twice as close to the other switch blade as it was before. And that's a big miniature of your cable listener.
So you want it open, you're adjusting it to remain open, but now you've got it opening late, which is what we want. We want it to open at the end, in the extreme, not soon.
Right, you want it to open as late as possible.
Open as late as possible. So, okay, we're just trying to find a switch.
I guess you're talking about flipper and stroke switches. Is that what we're talking about?
There we go. All right.
Thank you.
Hello, Sean. How are you?
Now,
Nice to see you in your Tempest. It looks like a Tempest. Is that your?
Yeah, they're stiff little guys.
Very well, thank you.
And Mr. iPad, who are you really, Mr. iPad?
I don't know how to change the name. It's Aaron.
Oh, Aaron. Hey, hi.
that's what you're saying. You want it to open as late as possible. That's the goal here, right?
Right.
If you know how.
Yeah.
Okay, I don't know why we're talking about flippers. What? Who's talking about flippers here? So hey, hi, welcome everybody.
Okay.
I guess, George, what I'm asking you to do, I guess, is look at, if you see participants in the waiting room, let them in. I guess.
There are 3 in the waiting room. Okay.
Oh, let's let those guys in.
Let them in. All right.
Please, yeah.
All right. We got Paul. Paul's here.
Oh, hi, Paul. Are you there?
Aaron?
Hello, testing, Paul. Paul,
Nice.
5, 4, 3, 2, 1.
What, your last name?
Aaron, do you need the old lady to help you out there? Hey,
Yes.
Thank you, Mrs. Aaron.
I'm an electrician by trade, but I mean, I can't figure out the iPad.
You know, it's interesting about that because I do not mess with my breaker panel. I absolutely don't screw with electricity. Electronics is not a problem.
Yeah, I'll play with that all day long, but I'm terrified to work on it.
Isn't that funny? So I'm getting a weird ringing feedback from somebody. So if you're not talking, try muting, I guess. I don't know who it is. And hey, Paul, how are you? Nice to see you, Paul. Hello, Paul. Hello, Paul. Getting a ringing feedback from somebody. If you're talking, try muting, I guess. I don't know who it is. Hello, Tony. I don't know who that is, but you've got some real low bandwidth there, obviously. It's.
You hear me?
Well, you're pinging and ponging, though. It's going. You hear me? Hey, John. You know what, John? I'm going to give John. I'm going to give John ultimate power George, because he knows what he knows. No offense, he knows what he's doing.
I just added like 4 or 5 people.
You do. Oh, thanks. That's good. Oh, well, now that you're the host, I can't unmake you the host because you're the host. You have to unmake yourself the host. So I don't know how you do that. Abandon host or make John the host. Make John.
I made you the host.
All right. Well, then I should be able to make John the host. There you go. So John, you're the host. How do you pronounce your last name, John?
McGacky's good.
McGacky. And would that be an Irish name?
Yep.
Yeah, cool. Cool about it. So hey, welcome everybody. I guess, and so John, keep an eye out for people that in the waiting room. I thought I configured it so that it was automatic and people could just come in, but
I got it.
Tony, what does she play?
It's on Minecraft right now.
Oh, is that intensive for bandwidth?
Oh, just for where I am. I'm just outside Niagara Falls, Ontario, and our bandwidth in the area is awful.
Oh, I've been there. It was interesting, and I was sort of disappointed because I've been there a couple times, and I really wanted to sort of retrace Tesla's footsteps. I really thought that I'd be able to go and see some original Tesla stuff, but as far as I could tell, there isn't anything to see. It's all Ripley's Believe It or Not and tourist crapola.
Yeah, a lot of that's all torn down. What they don't tell you about the area too is that there used to be a lot of refining for stuff. There was also a lot of uranium refineries and stuff like that all the way down along through. A lot of the spots for Tesla stuff and everything else were all torn down because they had radioactive waste in the actual landfill.
Oh. Yeah, we're still getting a weird. I am getting at least a weird audio. Is everybody else hearing the same thing?
Yeah.
Some weird
I have.
background hoodoo. I don't. Weird compression artifacts and poor old Zoom is probably trying to keep up as best as it can. But you can imagine half the world is using it, so it's a thing anyway. So welcome everybody, and thanks a lot for coming to this one. So I mean, if you've been following on the Facebook page, which is on the computer, I received this extraordinarily generous donation from somebody that said, "Hey, Randy, could we talk about vertical deflection, and he specifically mentioned Geo7, but it's kind of the same no matter what." And I put up that I uploaded a file. I don't know if you guys saw it or not. That's the one. Yep, that's it. Thank you very much, Aaron. That's exactly it. I spent a while researching that one before I wrote it, because in general, you guys kind of think that I know a lot of stuff, but generally speaking, I research it first and then I write about it, and then I know it. So I'm happy to cover vertical deflection circuits, I guess. But does anybody else have comments before I get going? Anything that they want to say? Maybe something about the possibility of this Florida thing coming up, which we could discuss or not if you want. Can't hear whoever said that. Paul, that must be you. Your bandwidth is terribly low or something. No. Paul, could you try logging out and logging back in again and see what happens? Because you're also sort of frozen.
No.
Because you're also sort of frozen.
Yeah, I am frozen.
Yeah. Okay. And I can hear myself echoing back as well. So Sean's laughing. He thinks this is funny. Sean, do you have some comment or something? No? Okay, that's fine. So Chris Lawrence, hello. Anthony, whoever you are, hello. Carl, hello. Larry, whoever you are, hello.
Hey, Randy, quick question. This is Anthony.
Hey.
You mentioned on a couple of your videos that you're posting the files. Where exactly are they going? Are they going on Facebook? I can't seem to find them.
Yeah, there's a place on Facebook. It's you just upload the file and it's there. I think I put it on the arcade game help repair group. or
Gotcha,
something
okay.
like that.
Okay,
But
I've
if you
been
can't,
looking-
but if you can't find it, drop me an email or something, and I'll be happy to shoot it to you somehow.
Appreciate it. Thank you.
Yeah, no problem. These are typically articles that I've gleaned from my big blue book of really great technical information available for purchase. But you know, as these things come up, you know, it's since I already have something in the can written about stuff that of this era, you know, might as well put it out there.
Appreciate that. Thank you.
Again, anything anybody wants to discuss. I hate to out this person, but oh, there it is, big blue book. Yes, that's right. Pages 162 to 168. Thanks. I don't want to out the person that made the donation if they don't want to be outed, but I wonder if this person is here, but I'm not sure how to ask without asking that person to out themselves. So I'm not sure how that's going to work. But let's talk about vertical deflection, I guess, if nobody has any objections. Cool. Everybody okay? Yeah. Thumbs up? Yeah. Okay. All right. All right. So, you know, there's lots and lots of vertical deflection failures. There's just a lot of them. And so let's just talk about that for just a couple of minutes. Hang on a sec while I switch over to the camera. And I'm as lame as anybody. Hang on a sec here. Switch to that there camera. There we go. All right. Stand by. I need to change my headset. This headset is a noise canceling headset, and I feel like I'm a deaf person. Like you know, you don't hear your own self talking, which is really weird. So, oh, sorry. Let me open up my Zoom window here so I can see what's going on. Hang on. Yes. Okay. Let's do this. Okay, John. Other John. So, one of the best ways I think to start looking at how the vertical deflection circuit works is to look at it in the form of a block diagram. And now that I'm saying that, I realize that I probably should take one step backwards, because in this lecture, we haven't really discussed the theory of operation of how monitors work. So give me just a minute. I know you guys mostly know this, but give me just a minute to talk about how the monitor actually makes the picture, right? So so there's the picture tube itself, and the way that the monitor draws the picture, as you likely know, is that it draws it one line at a time. It's really the only way it can do it, even these days with LCD monitors. It's a serial operation. It really draws things one line at a time. So the electron beam starts out in the upper left-hand corner and draws a line from left to right. And remember that there's the horizontal deflection circuit that does that. Horizontal deflection. And it's called deflection because there's the magnetic yoke that's on the neck of the picture tube that deflects the beam. That is to say, it pushes the beam, in this case, left or right in the horizontal direction. And as you know, the wide direction of the monitor is the horizontal direction. The short direction is the vertical direction. So it draws one line and it gets to the end of the line there, and it actually does receive a little sync pulse. It's either a positive going sync pulse or a negative going sync pulse. It doesn't matter. That's not this conversation. And then the beam retraces back to the left-hand side and then draws another line underneath the previous line. As you know, it only draws a line from left to right. Well, that the whole time the horizontal circuit is really just making the beam move left and right, there is the vertical deflection circuit that makes it move from the top of the screen to the bottom of the screen. Vertical deflection. Vertical deflection. So the horizontal deflection circuit makes it move left and right. The vertical deflection starts at the top of the screen and pushes the beam down, and that's how we get one beam, or one line, I should say, underneath the previous line. So in reality, the lines are really being drawn at a slight angle. That is to say, as the beam is moving from left to right under the influence of the horizontal deflection circuit, the vertical circuit is pushing it down simultaneously. It doesn't draw one line and then go ka-ching and go to the next line and ka-ching to the next line. It's continuously pushing the beam down. So it really comes down at a slight angle. That way, when it retraces, when we get the horizontal retrace that brings the beam back to the left-hand side, that line is underneath the previous line. So that's how we get one line underneath the previous line. And if you don't fully understand that, that's okay. My point is this, that the vertical deflection circuit, as you likely know, is the thing responsible for filling the screen from the top to the bottom. It gives us an entire, what we call a raster, a full screen full of something. And when we have vertical deflection failures, the kinds of thing you see that you're totally familiar with is this kind of stuff, where the picture might be like squished at the top, but normal at the bottom. That is to say, the top is actually compressed. Those horizontal lines that make up the raster lines that make up the picture are more closely spaced at the top than the bottom, and it's squished at the top. Or vice versa. You could have an image where the whole picture is normal up to the top, but at the bottom it's shrunk up like that, and maybe even the lines are real close together. You might even see where the lines have been folded over. As you know, there is a thing known as vertical fold over. It's called vertical fold over, where the top of the screen is literally squished and folded over, so that those lines that are normally at the top of the screen are bent over like this, and you see them backward, really, kind of on the screen. That is to say, they're kind of they are inverted there. So you might perceive that as something brighter on the top, but if you try to fill the image, make the image, the raster, fill the whole screen, the whole CRT, you can't do that. And very often, as you compress the thing, it does straighten itself out. But you have some kind of a problem where the picture is not filled from the top to the bottom. You might have an image that's only this big, just a little image like that, right in the middle. Or, as you probably know, you might have complete, total, catastrophic loss of vertical deflection, which just gives you the horizontal line on the screen, just a horizontal line, that's all, because there is no vertical deflection whatsoever. So if everybody's with me, the kind of the easiest way to understand how the vertical deflection circuit works is to start out looking at what's known as the block diagram. Something known as a block diagram. Actually, technically known as a functional block diagram. And what the block diagram does is it shows you the functions of all the circuits without really looking at the transistors and resistors and capacitors and the components. You're just looking at the functions themselves. So let's take a look at the block diagram for the vertical circuit. And that circuit begins, as you probably know, with a generally super reliable part or circuit known as the vertical oscillator, OSCI. LLATOR. Guess I should have made the box afterwards. The vertical oscillator. As you probably know, the frequency of the vertical circuit is 60 cycles per second. The vertical frequency is 60 hertz, 60 cycles per second. That's the same frequency as our AC power is here in United States of America and, well, all of North America and the Caribbean, really. Elsewhere, as you know, it's 50 hertz, but here it's 60 hertz. However, as you know, as you hopefully you know, the monitor doesn't depend on being plugged into the wall to get that 60 hertz. That 60 hertz is generated internally inside the monitor. And it's generated by this circuit called the vertical oscillator. The vertical oscillator makes this 60 cycles per second, this 60 hertz signal that eventually is what we call the sweep rate, the vertical refresh rate, if you want to put it in kind of computery terms, the vertical refresh rate, which is generally 60 hertz in, you know, most of the stuff that we have. And in fact, when you are adjusting the vertical hold potentiometer, which might sometimes be referred to as the vertical frequency, but probably not. It's just probably called vertical hold. What you're really doing is you're adjusting the frequency of this oscillator. You kind of get it in the ballpark. And as you know, there's this thing called the vertical sync signal that comes out of pin, well, the composite sync comes out of pin P of the JAMA connector. Anyway, there's a signal called vertical sync. And that vertical synchronization signal, vertical sync, comes from the computer itself, the game computer. And it tells the oscillator exactly what frequency and exactly what's known as phase, which is timing. Without the sync signal, the vertical oscillator will go at its own frequency, which you have determined by setting that vertical hold potentiometer. You kind of get it in the ballpark, and you see this happen actually when you adjust the vertical hold on a game. When it's not synchronized, you see that the picture is rolling vertically, and then as you adjust the vertical hold, all of a sudden it just snaps into place, doesn't it? It just locks right in place, assuming you have sync. And that's the sync signal adjusting what's known as the phase and the frequency of the vertical oscillator, so it's exactly timed correctly. The easiest way to think about phase is timing. Imagine a bunch of army guys, you know, marching, you know, and they're going up, 2, 3, 4, and they're all doing the same thing at the same time. They are all in phase. On the other hand, if they're out for the evening and they've had a few drinks and they're walking around in their civvies, they would be walking around out of phase. They wouldn't be marching around. So phase is timing. It's really timing. So anyway, so that's what the vertical sync signal does. And as you know, if you lose vertical sync, you will get a perfectly nice full picture, but it will be rolling one way or the other, either up or down the screen, as you probably know. So that's kind of how you know that you've lost vertical sync. If you can adjust the vertical hold and you get it really close, but it doesn't lock in place, you simply do not have vertical sync, which is not that common of a failure other than bad connections. It's usually not an actual failure. Anyway, so the vertical deflection circuit, remember we're looking at this block diagram of how it all kind of goes together. The vertical deflection circuit is kind of oscillating on its own at about 60 hertz, which you set with the vertical hold potentiometer. The sync will come along and lock it right in place. Hello.
Maybe Rich didn't go today.
Do I have a question?
There.
Okay.
Yeah, I saw that.
Then hello, whoever you are. Okay. So to continue. So now remember the final goal of this thing. I don't have the hardware here. If John, if you want to show us what a deflection yoke looks like on a G07 or something, that's fine. If not, that's fine. But as you know, the magnetic yoke, the deflection yoke that sits on the neck of the picture tube, has a couple of coils in it. It's really two pairs of coils. And the coil on the outside is the horizontal deflection circuit, and the coils on the inside are the vertical. You can think of it as one coil. It's the vertical deflection coil, kind of on the inside. Well, that takes a lot of current to drive it. That really is a very powerful magnetic field. and so the oscillator itself is really not powerful. It's precise, but it's not powerful at all. It can't possibly drive the yoke. It has to be amplified. And so following the oscillator itself, there's another stage which we refer to as the vertical amplifier. The vertical amplifier, and as the name implies, it takes the signal in. And remember, inputs are on the left, outputs are on the right. In a schematic diagram, inputs are on the left-hand side, outputs are on the right-hand side. So we've taken a vertical sync input, we've generated the 60 hertz oscillator, which is timed perfectly by the sync, but it's really weak. It's really precise, but it's very weak. It has to be amplified. So there's a vertical amplifier stage, which is some more transistors. So in every monitor that you're going to work on, except the K4600, the Wells Gardner K4600, this is all in one integrated circuit. This is all one integrated circuit. In the case of the G07, it's the HA11244. Is that right, Paul Jure? I think so. Anyway, so it's an integrated circuit that they refer to often as the television vertical horizontal integrated circuit. Because this integrated circuit contains not only the vertical section, but also the horizontal section, which is not the point of our discussion today.
11244. That's right.
Yeah. Okay. Thank you very much, sir. Appreciate it.
I have a deflection when you're ready, Randy.
Oh, you want to show it? Just do a share. Let's see it. Can I see it? Let's see how that works. Ooh, something's happening. There it is. Hey, great. So you can see that it's a sort of a magnetic coily thing. It is wound on what's known as a ferrite core. The grayish black substance you see there is made of something called ferrite, which is a mixture of ceramic and iron, sort of like a china plate with iron mixed in, baked in an oven. And the two coils that you see there on the top and the bottom, very good, Mr. Cursor. The two coils on the top and the bottom, they're the top and the bottom. Thank you very much. Awesome. So those are the horizontal deflection coils. Really, there are two of them, but they're in parallel, so you can think of it as one coil. And then on the inside of the yoke, where you can't see it, obviously, unless Paul has a yoke sitting around, he probably does have 20 of them or 50 of them. The coils on the inside are the vertical deflection coils, which have a much, there you go, that's cool. So those are standard colors, by the way. The red, blue is standard horizontal colors, and either yellow, brown or yellow, green is vertical. Yeah, there you go. Oh, there's good. That's a nice picture. Perfect.
Here you go, Randy. I got one
Thank
right
you.
here.
Yeah, I see it, brother. So perfect. So the coil on the inside, you can see it looks bigger, doesn't it? And that's because it is, and it's working on a much lower frequency. In the world of electronics, as frequencies increase, parts get smaller. So a coil you would expect to work at 60 hertz, which this is much larger than the coils on the outside, which are working at 15,750 hertz. So, you know, a whole lot. 240 times faster, 262 and a half times faster, or whatever it is. So anyway, so that's the vertical deflection. Okay, so back to my camera then. So the so the integrated circuit, typically it's an integrated circuit, or it's some discrete components, which it is in the 4600, the Wells Gardner K4600, which, by the way, used to be a Montgomery Ward's or J.C. Penney television. FYI, just to let you know, Wells Gardner made these televisions for J.C. Penney's and Montgomery Ward's. Those of you old enough to remember who those companies are. And you notice in the K4600, there's a bunch of parts missing, and that the board that you put the video into is different than the other things, and that was the modification that they made. Anyway, so So the point, so I'm sorry. So the point I was making is in that monitor, all these are not an integrated circuit. They're individual transistors and capacitors and stuff like that. Fortunately, that's been pretty reliable. You see more bad solder joints on that monitor than anything else. Anyway, so the output of the amplifier is still not powerful enough. Remember that we're going to eventually drive those coils that Paul just showed us, or John just showed us, or whoever was showing us, and they take a lot of current. So this stage then goes to yet another stage known as the vertical output stage. The vertical output stage. And in the G07 monitor or other monitors of that era, the vertical output stage consists of two transistors in the TO220 package. If somebody wants to show that, great. If you don't, that's fine too. Remember that this package is known as the TO220 package, as it's called. And there's a pair of those. Sometimes they're identical. Sometimes one is PNP and one is NPN. They are complementary, as they're called, but sometimes they're identical. And so those are the vertical output transistors. And certainly something that is highly suspect when you have a vertical failure. In general, in the world of electronics, I'm not just talking about monitors now, but in general, everything, it is outputs that fail the most because they work the hardest. Output transistors, output structures of any sort are the things that generally fail the most because they are the hardest working stuff. I mean, you wouldn't expect anything that's just kind of coasting along to fail, but if you have like a automobile engine that you're just driving at redline all the time and you're just pounding the heck out of this machine, you would expect it to fail. You just would. So same thing with electronics. Outputs fail a lot, followed by inputs. Inputs sometimes fail because they're subjected to noise from the outside world. But in general, the stuff that's in the middle hardly ever fails. I'm not saying it doesn't ever fail, but usually it's outputs. Maybe it's an input, but it's rarely the driver circuits and stuff. In my experience, I don't know. If someone wants to contradict me, groovy. I mean, maybe these days
Here's a G07, Randy, and there's the vertical ICs right there.
Okay,
So
we're not seeing it yet. Share screen, share something. There you go. Okay, you want to point that out to people with a finger? Just point it out with a finger. There you go. Perfect. Up, 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 up a little, up, raise it up. There you go. Those two. Tilt it toward the camera, please. Tilt toward the camera. Yes. Perfect. So anyway, so pair of transistors, TO220 packages, and no matter what kind of a monitor it is, if it's of that era, that's what you're looking for. If you're looking for vertical output, even if you don't have the schematic diagram, you can just go right for those things. They often do not test good in circuit. To be 100% sure, I used to try to leave them in circuit and test them because I thought I was awesome and a great technician, but I'm not apparently a great technician, and you really got to pull them out of circuit to test them properly. I know, Paul, you correct me if I'm wrong, because you do this way more now than I do, but in general.
I usually test them in circuit, and they usually test fine, and I just move on from there.
They test perfectly okay. Nothing weird.
Well, no, nothing weird. They seem to test fine for me. I'm just looking for a short on them. If there's no short, I just move on to.
You're mostly correct, 99.9% correct, probably, but that attitude has screwed me up.
Oh, yeah.
That's kind of what I was talking about, where for a while I used to think I'm God's gift to the world of repair. I'm just a great technician. And boy, oh boy, nobody can be better than I am. And then I was not finding problems. And then I was like taking parts out and checking them out of circuit. Oh, junction drop both ways. Oh, that's a weird failure. How does that happen? Should be open one way, junction drop the other, right? So that's my only point there, is that sometimes you can hose yourself.
That's something I didn't know. You learn something new every day.
But maybe I'm just being paranoid about it, because I'm talking about, less than 1% probably of the time. But I guess having seen it, it just stays in the back of my mind. All right. So anyway, so So the output is the pair of transistors, or it is a separate integrated circuit. For example, in the K7000, it's this is IC3, isn't it? Right, the vertical output integrated circuit. But in other cases, it's a pair of transistors. And it's easy to suspect that this is bad. When you have a horizontal line on the screen, those of you that do the shotgun procedure where you're just gonna, just tell me what to change, I'm just gonna change it all. That's the first thing you jump on, but there's some things you need to kind of look at before you jump on that, just so you don't frustrate yourself. There's some easy tests that we want to make first, and we'll talk about that in just a little bit. So the output of this thing then goes to the vertical deflection coil that's in the yoke. This is sometimes abbreviated on the schematic as VDY, vertical deflection yoke sometimes, but it's the vertical deflection coil. And really, it is really a pair of coils wound in series. They're connected in series, I should say. And so the output of whether it's a chip or the pair of transistors, drives the vertical deflection coil. Now, as you may know, if you know anything about electronics, the way an electronic circuit works is that you have some sort of a source of a signal or power or something. You have a path that takes that signal to what we call the load. In this case, the load is this coil. And then you have some sort of what we refer to as a return path. Again, it is not the point of this lecture to talk about complete circuits, but the current has to go somewhere. And generally speaking, what that somewhere is ground. And as you know, in most of the monitors of the era we're talking about, it's really a chassis ground. It goes to the ground, the chassis ground. However, in this case, in the case of the vertical output, the vertical deflection coil is not directly connected to ground typically, or ever, I guess, really. There is a capacitor here in series with it. And it's an electrolytic capacitor, and the value of that capacitor depends on what era of monitor we're talking about here. If it is the type of monitor that has the pair of vertical output transistors, then that is typically 100 microfarads at 160 volts DC or so, typically. And it's a common failure. It's one of them common failures that when you have a problem where the screen is getting smaller and smaller and smaller, that's one of the first capacitors you definitely hop on and test the ESR of that capacitor, not its microfarads, but its equivalent series resistance. And again, it's not the point of this lecture to talk about how to test capacitors, but if you're serious about doing this and you just don't want to be a shotgunner where the only way you can test a capacitor is by sticking in a new one, you need to get an ESR meter. You have to have an ESR meter. You can build a little kit for $10 that's an ESR meter, or you can spend $220 on a really good, awesome ESR meter, which is what I recommend. But you have to have one anyway. So it will either be that value, or if the vertical output is the integrated circuit, like IC number 3, for example, that works at a much lower voltage. That's only working on 24 volts DC. And the value of that capacitor won't be 100 microfarads at 160. It will be something like either 1,000 microfarads at 25 volts, or it might be 2,200 microfarads at typically 25. It might be 35 volts, depending on what it is. But it's some much larger capacitor. And same story, if you have a problem with loss of vertical deflection, where the screen is getting smaller and smaller, typically over time, that's one of the capacitors that you definitely want to test and or replace. Anyway, so that's the entire block diagram of how the vertical circuit actually works. So anyway, if that's cool, before I erase this, does anybody have any specific questions about this so far? Because I'm about to get into the schematic diagram.
So story.
Sorry?
Can I tell a story?
Yeah, let me sit down. Give me a minute. Sit down here. My coffee's cold. Yeah, go ahead.
Spotlighted. Look at that. Okay.
Yeah, if you talk, it shows you.
Okay. So last year, I had like a guy that runs an arcade. He referred me to somebody that had a monitor issue. And it wound up being a Geo7 from a Defender. And what it was doing was, let's get my hands in the picture. The top half of the screen was like doing one of these, where like that's the top of the visible picture. It's like towards like the middle, right? And so I go to the guy's house, I get the chassis, and then I bring it to work on it. And as I'm like recapping it, I pull, is it the 400 section that's the vertical section of the Geo7?
Yep.
Okay. I pulled a cap out of there. It was like a big one. I don't know. Is it 2200 maybe?
Oh yeah, that's at the edge of the chassis. 2200.
Yeah, I don't remember the number of it, but I took a picture of the cap after I pulled it out, and you can see that it was like all leaking out and whatever else, right? So I'm like, well, okay. So I recapped it, and then I threw it in a game over, you know, at the shop there, and it looked fine, right? But then like I take the chassis and I bring it back to the guy's house, and it starts doing it again, right? And I'm like, well, okay.
Yoke problem, maybe?
No, it pertains to this subject perfectly, because it actually wound up being the two vertical deflection transistors that were bad on it.
Huh.
And you tested them and they tested good?
I didn't do any testing. I just
okay.
swapped them out. But there's a guy on KLOV. He's like a Geo7 expert. I asked him about it, and he was like giving me about like 10 different things that were apparently not related to this, right? And I had like a junk chassis just laying around. I just stole the parts off of that and put them in there, and then it worked, you know.
So my comment here is this, and I was going to get to it. And George, it's great. It's a great story because it's perfect. I have had more than once the TO220 package vertical output transistors test perfectly good, even out of circuit, just using a meter, not with any sort of XOR size or a real thingy that operates the transistor, and had them be bad. And finally, after giving up basically and replacing the integrated circuit and everything else except the output transistors, which I was certain were good, I went, oh, what the hell? The only parts left are these output transistors. I'm just going to change them. And that's exactly what it was. So, you know, as a technician, I can't explain that. As an engineer, I probably could, but I'm not. So, you know, all I know is that in my personal experience, and, you know, like Paul, he fixes just a ton of monitors all the time. It's what he's doing, and I was doing it too. So is this a large percentage of the ones? No, very rarely, but it happened again. So same sort of thing. Whereas a technician, I just kind of keep that stuff in the back of my head, and maybe it screws with me and maybe makes me a better tech. I'm not sure.
Well, to like elaborate on that, you mentioned something about like, you know, components stressing other ones. I'm gonna guess that that like rotting cap probably had something to do with it. It must have stressed.
You know, I didn't say that. I don't know what I don't know where you got that, but that's not generally. That is not. Oh, it happens sometimes. I shouldn't say that because I know a couple of conditions where it does. You know, generally speaking, when the cap just fails, it opens circuits and goes up in resistance, in its equivalent series resistance. So typically, it causes symptoms, but it doesn't blow anything out. Typically, because it causes voltage to drop, not go up. Typically, there's a couple of exceptions to that rule. So anyway, all right. So if we're ready to move on, let me. I'm just going to cover a little bit about the output circuit in kind of general on the board, and then I think I'll move to the schematic diagram. Yeah.
I have a quick question.
Yeah.
Keeping in mind, I'm still complete noob to all of this, but I read the the thing you asked us to download. And on page 163, it mentions a blanking circuit.
Yeah.
So that as it's going across and when it reaches the bottom to come back up and start over again, when it finishes the field and it's starting over again, it mentions a blanking circuit so that there's no retrace as it's going from the top back up to the bottom.
Correct.
Now, if I
Retrace
understand,
lines.
I just want to make sure I understand this correctly. So as it's going side to side, there's no blanking circuit on that horizontal. It's just a continuous beam. It's only when it's going.
No,
from
there
the
is.
top.
There's horizontal retrace blanking and vertical retrace blanking.
So
When the
as
beam-
it's going across, when it hits the end to come back, it's turning everything off and then redrawing it again.
Correct. It only draws from left to right. At the right-hand edge, all three guns, if it's a color monitor, are turned off simultaneously. The magnetic field itself resets to bring the beam back to the left-hand side. And once it reaches the left-hand side, and one of these days we'll talk about how it does, how it knows that, it turns the beam back on and draws the next line. Then when it's done drawing the entire field, as it's called, the entire screen full of lines is called a field. When it's done drawing the field and it has to shoot back up to the top and it really zigzags its way back to the top, we certainly don't want to see those vertical retrace lines, as they're called specifically.
Okay, so there is both a horizontal and a vertical blanking circuit.
Yes, sir.
Thank you
Well,
very
there's
much.
a blanking circuit, and there is a blanking circuit, and it is triggered by both the horizontal retrace and the vertical retrace.
Okay, so it's just one circuit. It's not. There's not two. One that's specific to either one. It's a universal.
Well, if you think about, not to digress, but we are digressing a little bit.
Sorry.
No problem. The purpose of, I think I could do this without going to the board. The purpose is to turn off all three electron guns at the same time. So you wouldn't need two different circuits to do that. You just have one circuit that turns off all the guns, and two different things are talking to it through capacitors, horizontal and vertical.
Got it. Cool. Thank you very much.
All right. So let me go back to the board then, and let's and then as I mentioned, I'll move on to the schematic in just a minute here. Oh, Canada, my home and native land. All right. Except it's not my native land. I'm Canadian, but I wasn't actually born there. Okay, so so let's look at the output circuit itself. Let's hang on one sec here. So let's look at the vertical output circuit. Just kind of a not exactly abstract way, but this is not perfectly like what the schematic is. So the way the vertical circuit works is this. Typically, we have some sort of power supply voltage. It might be 24 volts. It might be 120 volts. There's a bunch of things that it could be. And again, this is a super simplified look at it. And there are two transistors here. These are the two transistors that are in the TO220 package. And typically, not always, they are arranged more or less like this. And again, I'm just being, I don't know what the word, not specific about this, I guess. And so, and then this side is connected to ground. Clearly, if this top transistor is turned on, let me grab a different color pen. If this top transistor is turned on, the electric current will flow from whatever this positive power supply is into the collector, out the emitter here, because it follows the arrow, right? And like in that direction. Well, this right here, where these two guys are connected together, is where the deflection coil is. So here is the vertical deflection coil that's in the yoke. All right. So we want to send current now out to the deflection coil like this. So that makes the thing, energizes the coil. And of course, it builds up a magnetic field. And that magnetic field is the thing that moves the beam down from the top to the bottom of the screen. At the same time, current is flowing into this capacitor right here. And this is the capacitor that I mentioned earlier. You can kind of think of this as the AC return. That is to say, a capacitor will block direct current, but it will pass alternating current through it. If we had a DC return here, it would wipe out these transistors. It would just blow them like instantly. So then the current flows, through this guy to ground. And now here's where I'm a little unsure about the total theory of operation. And if somebody else knows this better than I do, I'm absolutely welcome to have somebody else explain this. Naturally, both of these transistors cannot be on at the same time because that would short the positive side to ground. So this guy is now turned off. This transistor is turned off. This bottom transistor is now turned on, and you can see that it is completing the ground. When this transistor is turned on, current will flow through this transistor to ground. It is a ground switch, as it's called. It's a ground switch. Well, after the current has flowed through the coil, it has started.
I think you lost your microphone.
Testing, testing, testing. No,
You're good. You're good now.
okay. Wow. When the current went through the coil, through the capacitor, this capacitor is now charged up. Well, now this transistor is turned on. This one's off, and this one's on, and that is the source now. And this is discharged to ground, and that's what causes the beam to fly back up to the top again. So as this thing is discharged, the beam goes but quickly back up to the top because it's discharged really fast. When this transistor is turned on, it's building up the magnetic field and making the beam move from the top of the screen down to the bottom, if that makes any sense to you. Well, remember that the base of the transistor, this is called the base, as you know, is the controlling element of the transistor. We control the transistor by putting current on the base, by putting some juice on the base, basically. But in this case, this base is the thing that's connected to the vertical chip, the vertical amplifier. Remember, that's part of the chip. Remember, that's the amplifier output there and the vertical oscillator that's also in there. The important thing to remember about a transistor is that it's not so much the voltage that is specifically on the base that turns the transistor on or off. It is the difference between the base and the emitter. That is to say that in an NPN transistor like this, the base has to be 0.7 of a volt higher than the emitter in order to turn the transistor on, because it's an NPN, meaning the base region is made out of type P silicon, and you got to put positive juice on it. So there are two different ways you can control a transistor. You can control a transistor by putting a certain amount of voltage on the base, or if you hold the base constant at a certain voltage, if you modulate, as that is to say, change the voltage on the emitter, that also can control the transistor. So what happens now is that the emitter voltage here is the thing that's really controlling this top transistor, turning it on and off. The bottom transistor, you can see, is controlled by the amplifier chip. We'll take a look at the schematic in just a bit. So what's turning the top one on and off? Well, it's the voltage at the emitter of the transistor as it is modulated that controls what this transistor is doing, if you care. So there's a couple of things that you need to look at when you have loss of vertical deflection. One is, do you have this voltage? Do you have whatever the positive voltage is there? We're going to look at the schematic diagram to see what it is. And the other thing is that this integrated circuit also needs to have some sort of power supply. And this integrated circuit is half vertical and half horizontal. And there are really actually two different power supplies. There's the plus vertical power supply and there's the plus horizontal power supply. It's two completely different power supplies. So when you're working on this kind of a thing, just be aware of that. Even if you've determined that the horizontal power supply is there, it doesn't mean the vertical one is there. So, and that vertical power supply sometimes is a flyback derived power supply. So if it is a flyback derived power supply, you know that we have lots of problems with those. The capacitors in the flyback derived power supplies fail all the time because they're working at a really high frequency. So that's, as you know, Paul, and anybody else that's working on these monitors, anytime you see capacitors near the flyback transformer, you're for sure changing those things. I mean, you're probably changing them all anyway, but those are, I mean, if those are even 5 years old, they're probably bad, and let alone 40 years old, right? As you know, if you have a Pac-Man that's made in 1980, you're keeping monitors alive that are 40 years old now. And, you know, so anyway. So if that makes sense or doesn't make any sense, oh well, let's take a look at the schematic diagram and let's see if we can just kind of take a look at what the parts are. Does anybody have any questions so far?
I just like to say it's a pleasure to get one of those 40-year-old monitors that nobody put their hands on yet. The original capacitors and all the original solder and nothing that's been manhandled on them.
How often does that happen these days? To you, Paul? How often does that happen, Paul?
Quite often. I'm constantly getting virgin chassis in here that nobody has touched that still have the original capacitors on them.
Wow, that's cool.
There's a lot of Go7s out there still.
Well, they made a crap ton of them, that's for sure. I mean, I like that monitor. I like it a great deal. I think you certainly, once you're familiar with that, it makes your life easier, that's for sure. All right, so let's see.
I've had quite a few Go7s that actually didn't, you know, they needed caps in the sense that there was cap related issues, but they still ran. So
isn't that
a lot
amazing?
of credit for that one.
Yeah, no kidding. I agree with you 100%. I think it's just amazing. I think it is just absolutely amazing that some of these really, they kind of really work. You know, they just kind of work. Okay, so let me try something here because I'm not that awesome at this Zoomy thing. Hang on. So am I sharing this screen? Can everybody see this? Do you see the schematic?
As you're sharing, there it is.
Everybody cool on this? No? Yes? Are you seeing the schematic, folks?
Yeah, you're good.
Okay, thank you very much. All right. So, I guess it might be... Yeah, I suppose you could open up your own schematic and follow right along. Huh? So when I am looking at the vertical, or any section really, deflection section, the first thing I kind of look for is the yoke itself. And if it's a properly drawn schematic, the vertical deflection coils are in series and the horizontal deflection coils are in parallel. I have, however, seen, I'm not sure, I think it's the K7000 that's wrong, that they've got the vertical as parallel and the horizontal as series. But anyway, so that's kind of what I'm looking at for there. And usually it's labeled VDC, vertical deflection coil, or VDY, vertical deflection yoke, horizontal deflection coil, and like that. So what I typically do is try to follow that back. In other words, what I'm giving you now is a clue as to how you can figure out what this is, you know. And so I look at this and I say to myself, well, gee whiz, I have no idea what this is. I can recognize the yoke. Let's see where it's connected. So if we follow the cursor, if you're following my arrow cursor back here, following it back here, and right here I get to a junction of a 2.2K resistor. Well, clearly I'm not going to get any current through a 2.2K resistor. That can't be my path. So let's go up and see, oh, here's my path. Okay, so here's a path. Let's see, what would happen if I went left? 27K resistor. It's not coming through there. Let's go to the right. Oh, look, what a surprise. there it is. So there's the vertical output pair, and it almost always looks the same when it's discrete transistors, individual transistors. Typically when they draw this, they stack one on top of another, and it looks, just like this. Right. So as I mentioned on the board, the output here, this is the output where the two transistors are connected together, and that's just a 5.6 ohm resistor. Never seen that open. Paul, have you ever seen that open? I can't imagine it would.
No, I haven't.
Nah. Resistors are the last thing you test, by the way, just to let you know, in general. There's some exceptions, but in general. So the output comes from there and goes to, let's follow the cursor down here, goes to the deflection coil. So there's the deflection coil, right? Now, let's see where the other side is, the return path, because that's where we do have some failures. So here's the return path. This is after the current has passed through the deflection coil. Where's it going? It's, it's going to head to ground somewhere, right? So if we follow this guy up and over to here, and remember I mentioned this value to you, the 100 microfarad, 160 volt value, and that's pretty common. Sometimes it's 220, but usually it's 100 and 160. And that's always a capacitor you want to replace, always, always, always. It's, when I was working in the field, it was always a capacitor I carried with me just because I would throw it in the field. So this somehow now has to go to ground. And in this particular monitor, it does something pretty interesting. So let's follow this now. This is the signal that it needs to go to ground somewhere. It's headed to ground. And it goes through something, in this case, called the side pincushion transformer. And I'll get back to that in just a second. I'll get back to that. So it goes through that thing, which is very low resistance. It's just a couple of turns of wire, basically, and goes over here. And there's a very low ohm resistor that goes to ground. This is pretty common. And I have seen this resistor increase in value once or twice. And it causes, as you can imagine, the screen to get less tall, narrower from top to bottom. In this case, it's 6.8 ohms. Sometimes it's 1.2 ohms, might be 4.7 ohms. Typically, it's like a watt. In this case, you can see it's 1 watt. It's a ceramic metal film resistor, non-flammable kind of resistor, like that. So that's our return path to ground. So if you had bad vertical deflection where it wasn't filling out the screen properly, or it was compressed, or something like that, if you had some vertical deflection, then chances are that these transistors are good. If you have some, Paul, correct me if I'm wrong, if you have some vertical deflection, 3, 4, 5, 6 inches, half the screen, or whatever, it's been my experience that these transistors and that diode are good, and that you have a bad capacitor somewhere. Paul, is that correct in your experience?
That's correct for the most part. I've seen some odd failures where one of the transistors will be partially bad, and you'll get 3/4 of the screen though.
Right, and we talked about that a little earlier, right? So it might be that, but typically that causes complete loss of vertical deflection. And so if you had some vertical deflection, it's again C411 in this particular monitor, but it's some 100 microfarad, 160 probably. So in this case, the return path is through that capacitor, which when its ESR increases and it goes bad, doesn't allow enough signal through amplitude, really. And it wants to go through this resistor to ground, but at first it goes through this thing called the side pincushion transformer, which is kind of unique to this particular monitor. And as you know, when you have these weird problems with what's called trapezoid, or where the sides of the picture are like pulled in, you always want to replace these two capacitors, C518 and C517. That's always included in the kit. And that's also a very, very common failure. It doesn't cause loss of vertical deflection, though. It causes the sides to pull in left and right. Now, the reason there are two capacitors here, you might say to yourself, hey, well, this one's 220 and this one's 100. Couldn't I just put a 330 in there and make it so, and you can actually, and that works really fine. The reason they put 2 in there is to lower the ESR. I keep talking about ESR, and it's an important characteristic of capacitors, not what we're talking about today. But if you put a bodacious, really good, nice Nichicon low ESR capacitor there, no problem. A 330 works fine.
I always wondered about that. Why did they have those 2 capacitors there instead of just a 330 UF?
Yeah, now remember this is 1980, so electrolytic capacitor technology has gotten a lot better. ESRs have dropped like a rock on even common electrolytics due to advanced etching techniques and electrolyte chemistry changes and stuff. Anyway, so if I'm ever working on a different kind of monitor and I see that the sides are pulled in on the sides, and maybe when I get back to the board, I'll show you what pin cushion or trapezoid distortion looks like. I'm always looking for this. I look for this side pincushion transformer. This is not what we're really talking about in this lecture. And I look for capacitors that are across it. Anyway, so here is the chip that I was telling you about. The bottom half is horizontal. This whole bottom half, the phase detector, the horizontal oscillator, the waveformer, that's the horizontal part. It has nothing to do with what we're talking about here. These are 2 completely different circuits. They're just like totally independent and even have their own power supply, which you can see right here on pin 6. So here's the deal here for the uninformed, that this thing needs a 10-volt power supply for the vertical section to work. You definitely want to check pin 6 to see if you have that 10 volts. And it's usually there. Paul, have you ever seen it not be there? Have you seen the shorted Zener?
Maybe once or twice, but not very often.
Right. Usually that voltage is there, but it's something before you change the chip, for God's sake, you want to check it, because, follow me here, we're going to go back to the right-hand side where this comes from. So following this dashed line here, here, you can see it comes from a flyback derived power supply right here, this power supply right here. And so that's the 12-volt supply. If you are missing this 12-volt supply for some reason, obviously the chip's not going to work. So that supply comes from here, and you can see here's the filter capacitor for this thing. So there's a 4.70 1-watt resistor that is in series with the winding. Certainly, if that resistor were to fail, it would open circuit. I've not seen it, but it's in other monitors like the K7000. Oh, it's really common. It's R91, R92, and it's only 1.2 ohms, if this is ringing a bell to you guys. And very often that opens circuits. When you lose the when you lose the vertical output chip, that resistor, which in that monitor, which is not what's in front of you, is 1.2 ohms, open circuits. So that resistor, in this case it's 4.7 ohms, is used to cut down the voltage a little bit. And you might ask yourself, well, why didn't they just make this winding the right voltage? Why did they make it too much voltage to the point where they had to cut it down? Because you can cut down voltage, but you can't add it. So if they make this thing incorrectly and the voltage is a little bit too low, they are hosed. Where if they make it and the voltage is a little too high, which they do intentionally, they can then cut it down with a resistor before rectifying it with a diode. And this, I've not replaced this diode. It's a high frequency diode, a fast recovery diode. Paul, you've never changed this diode, have you?
I don't recall, probably not.
And the filter capacitor, so there we get our, it'll be about 15 volts here. They run it through another resistor to cut it down, 68 ohms, 2 watts. And again, I've never seen that fail, but if it did, it would open circuit and cut out what they call the B2 voltage, the 12 volts that powers the chip. So if for some reason you had total loss of vertical deflection and it wasn't these transistors, and you didn't see any bad capacitors, you certainly want to measure that voltage at pin 6 there and see if you have that voltage. The only other thing that could fail other than the resistors opening is if that Zener diode were to dead short, and that's how Zeners do fail sometimes, it would drag that voltage down to a volt or two probably. And also you would lose vertical oscillation. You'd lose that whole vertical thingy. Anyway, so here's the output of the vertical amp at pin 2. And I've never seen this chip fail other than us blowing it out in a lab one time semi-intentionally. But pin 2 is the vertical amplifier output of this thing. I don't think you really care about this, but if we follow that output up and to the right, 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 through just 680 ohms, don't know why that's there, and it goes to the base of the bottom transistor. So remember I mentioned to you that by modulating or changing the bottom transistor, when we drop that voltage down, it changes what's called the bias on this upper transistor. So you really are controlling both the transistors at the same time, but the output of the chip only goes, so wake up, only goes to X402, if you care. And so there's one other thing that's super important here, and that is this tantalum integrated tantalum capacitor right here on pin 5. This is very important. I think it's 2.2 microfarads. I can't really see it. I think it's 2.2, 16 volts. Tantalum capacitors are interesting because they pack a lot of density in a small package, a lot of microfarads, you would say, in a small package. But they're also thermally stable. They're a very stable capacitor until they crap out completely. And when they crap out completely, they can do weird stuff like short circuit. Electrolytic capacitors typically do not short circuit, but you should be aware that tantalum capacitors may short circuit, not necessarily in this case, but in some cases. So this is used for stability for the oscillator itself. So this is definitely one that you want to change. I have thrown in electrolytics all the time here, and I've never had a problem. Paul, do you use a tantalum here, or do you use electrolytic?
I've never seen that one fail, so...
Oh, you've never even changed it?
No, I've never changed one of them.
Wow. Okay. Well, it's something that I change because, hey, I know it's in the vertical circuit, and what the heck? Like you said, somebody said it's the 400s, right? The 400, number 400 parts and vertical parts. So, but I can't say I've ever fixed something by changing that. Yeah, it's been a long time.
So you said you replace it with an electrolytic?
Yeah, I've replaced it plenty of times with electrolytics. Okay. I've never had a problem with the monitor not working. Now, how the monitor reacts in 5 years, I don't.
So is this capacitor?
Sorry. Go ahead. Hello. Is this
Can't hear you.
Hello, me? Did I break my? Can you hear me? Hear me? Hear me?
Are you there?
I can hear you, Randy.
I can hear you.
There we go. Testing 1, 2, 3. Ah, that was weird. Okay, everybody cool? Hear me? Yes?
Yep.
Okay, good.
So that capacitor is polarized then, right?
Oh, I'm sorry. Yeah, it's polarized. It's just a regular capacitor.
Okay.
Okay, there we go. Okay, so, but the other thing that I look at is this, and you guys do too, I'm guessing, and that is I say to myself, oh, I'm shrugging to myself. I'm shrugging my shoulders going, gee whiz, I've got some kind of a weird problem with the vertical section. Wouldn't it be prudent to change 412, even if I don't know what it does, which I don't? Wouldn't it be prudent to change C408, even though I have no idea what it really does? Yes, it would, right? So that's all I do. I mean, I'm not the sharpest tool in the box, and sometimes I'm just grasping at straws, trying to figure out, what's really going on. So there's also a feedback loop here, and that comes in pin 3. If you notice on pin 3 of the vertical amplifier, it has an arrow pointing down, right? So that's an input going into the thing, and that's feedback. And we may get into a discussion of feedback in the future. I'm not going to talk about it right now, but something has to tell this circuit what's going on in the output. if you just tell a circuit how to behave and trust that its output is going to be good, there's all kinds of things like temperature and stuff like that that can affect the output, and things will drift like crazy. You have to have feedback, and usually it's what's known as negative feedback. And that's what we have here coming into pin 3. And if you look, what's pin 3 hooked up to? Oh, look, it's hooked up to these potentiometers, which are the vertical height potentiometer and something known as vertical linearity. And the linearity, as it's called, is the spacing between each raster line. It's supposed to be the same from top to bottom. If the picture is squished at the top and stretched at the bottom, you have poor linearity. So the only reason I'm mentioning that is that a lot of people just hop on the potentiometer itself. If whatever function the pot is supposed to control isn't working, they automatically think the potentiometer is bad. And that's the last thing that I suspect, unless it's physically broken, unless it's really physically broken. Typically, the potentiometers aren't really bad. Paul, are they going bad now?
Yeah, this late in the game, I replaced quite a few of them. These old metal potentiometers on these Geo7s are starting to fail and just literally fall apart at you trying to turn them. They'll just fall like three pieces.
Oh, well, that would that would say replace me, I suppose.
Yep.
Okay. All right. Well, in my real world experience, it hasn't been so. So anyway, so that's kind of my lecture on the vertical circuit, I guess, of Geo7, and we can go over it again in another presentation, and I can go over the K7000, which once you know this, the K7000 is pretty easier, but I'm getting just a little bit burned out today. So I may call this to a close unless somebody has some cool, fun things you want to talk about.
Just one more thing on the vertical circuit of the Geo7. Whenever I rebuild a chassis, I get a chassis come in and rebuild, I always replace FR401 now. They, for some reason, for some reason, the way they built them, they get this, it looks like, kind of looks like they were eaten away or rusted away, or they have this like greenish
Green stuff.
to them. Yeah. And they just literally fall apart now. So that's a must. You have to replace FR401 pretty much every time, because the legs are literally just fall off the resistor.
Oh, how interesting. That's 68 ohms, right? A watt.
Yep.
Like
Yep.
Yeah. Okay. Well, that's always nice to know. And Paul, I'm sure grateful for your input. And if we do the Florida thing, I'll certainly contact you. It'd be fun to have you on board.
Yeah, that would be awesome.
I don't know. You guys probably read the thing about the thing in Gainesville, Florida. I don't know. It might be a really fun enterprise, but I got to figure out what to do, because I don't want to do it if it's just a repair gig. I gotta include a school with it somehow. So we'll see how that goes.
I've always wanted to attend one of your classes.
Well, you'd be welcome to come. That's for sure. They're pretty fun. They're mostly fun because we're a room full of nerds that are just like us. It's kind of cool. We're not talking about sports or even car motors. We're talking about games and electronics. It's pretty much fun. Anybody else have any comments? George, Carl, anybody? Aaron?
Are you still doing the classes that you were just talking about?
Well, I haven't done one since last November, November 2019, when I did one in Holland, in Netherlands. I haven't really done an amusement class in quite a while. My concentration has really been on the casino industry. I'm teaching slot machine technicians, mostly Native American people on the res, how to do electronics and how to repair LCD monitors now. It used to be CRTs, but they haven't used those in ages. But I'm amenable to doing amusement classes. The issue is always for people who are hobbyists now to take the time off of work for their hobby, and also the venue, like where are we going to hold the class? It has to be somewhere where there are games to mess around with and like that. So
did you ever try offering your services to a show that goes on? There's plenty when COVID's not around. There's plenty of hobbyist arcade shows all over the country.
Oh yes, I was in contact with the Midwest Gaming Show, and that one looks like a great enterprise. And just before this hit, we were going to do it. It was all good. It was all planned. Well, tentatively planned out, and then this hit. So I mean, people are getting vaccinated now. I'm over 65, so I've got my first shot. Next shot comes in a couple weeks. I'm hoping by fall, of this year, things can start to get back to normal. At least we all know how to wear masks now, and our president's not telling us not to wear masks, which is a good thing.
Did any of you guys? Would any of you guys attend the what was that California Extreme?
Yeah, California Extreme's awesome. That was gonna be my suggestion too.
Oh, hey Jay, how are you?
Hey, how's it going?
Fine.
What are some of the other events? Paul, you said there were stuff all over. Like, what are some of the
Down
events?
here in Florida, we got Free Play Florida. We got an event in Jacksonville and an event in Miami. Nothing going on now, obviously, because of COVID, but there are 3 events down here in Florida.
There's also a big one in Banning every year, I think a couple times a year that they have quite a few. There's a lot of pinballs there too, but a lot of videos.
Oh yeah, and Banning, yeah. Which is right near Coachella. If you want to do both of those things, you can. I think, isn't it? I think anyway. All right. Hey, well, listen, guys, I'm gonna stop it. Oh my God, did I turn on the recording? I hope I did.
Yeah, it's recording.
Okay. Phew-wee. Holy cow. All right. Well, I'll say goodbye to everybody. Aaron, do you have another comment or something?
Just another quick question. Like I said, I'm a noob to all of this, and I'm an electrician by trade. I mean, I've worked on live electrical panels in the rain and not thought twice about it because I have training and experience for almost 20 years now doing it. So when I see Sean holding up a yoke from a monitor, I'm like, how did you do that without killing yourself? Where's
the yoke? Yeah, the yoke isn't where the voltage is. But
no, but see, for me, it's like I'm afraid to put my hands on any part of the monitor. When I see Paul holding up the whole chassis, I'm just like, again, it's so. Where can I go just to start learning basic safety for just charging stuff and so that I could take one apart and feel comfortable putting it on a bench and messing around with it?
I mean, for the best thing is really for you to look at my videos. Have you seen the video that I did on CRT monitors?
Is that one of the ones from what we're doing now?
No, on my YouTube channel, there's a video on understanding CRT monitors that you should watch. And at one point in the video, I plunged my hands into a monitor all over the place and touched a crap ton of stuff to show you. But I think it's interesting, and you're not concerned about flashover, but you're worried about touching the yoke. So I think that's
well, no, because like I said, I not being new to this, I don't know what parts I can and can't touch, where voltage is going, and stuff like that. So I recently subscribed to your YouTube channel, so I will make that part of my.
Yeah, look under the videos where it says the list of videos. Unless I'm sure they're up there. So, all right, listen, I'm gonna stop all this. I'm gonna turn off the recording and.
You're the host now, Randy.
Okay. Oh, good. All right. Thanks. Appreciate it. And sayonara, everybody. Thanks for joining me, and I think we'll probably do it again next week. See how it goes.
Okay. See you next week, Randy.
Thanks, Randy.
Thanks, Randy.
Good to see you.
Thank you.
Stay safe, everybody. Good to see y'all.
Thank you. Bye-bye.